Hello and welcome to my C++ metaprogramming talk with a hint of reflection. So who am I? I am a C++ enthusiast and I am currently 14 years old. I have a GitHub, which is where I have lots of my libraries that I maintain. Most relevant to this talk is mlib, which is a C++ metaprogramming library with a hint of reflection. If you'd like to reach out to me, you can reach out to me on my email, rshepherdcpp@gmail.com. The outline of this talk. What is template metaprogramming? General metaprogramming, metaprogramming using tuples, some cool metaprogramming things, making some standard library containers constructor using metaprogramming, a bit about my metaprogramming library, and some reflection, which is a small but very powerful example of reflection. Okay. The layout of the slides. The full code will be shown with a brief introduction of what it does. There will be then a small walkthrough of the code. Then a benchmark will be shown, normally. Then the links to the godbolt and the benchmark will be shown. So what is template metaprogramming? Here's Wikipedia's definition. So it basically says that templates are used to generate temporary source code and later on it goes on to say it's known for being C++, which is what this talk is about today. So metaprogramming using subtuple. So subtuple, making a small tuple out of a tuple. So I will show you the full code first. So the template. So it's a templated function taking in two indexes and the parameter back. So the v represents the starting index of the subtuple, and the t represents the ending index of the subtuple. So then we have the function labeled as constexpert and takes in a subtuple t. So first of all, we static assert that the last index of the subtuple is less than the size of the tuple, and we should also factor in more static asserts, but just slide where I decided to leave those details out. Okay, so then we have an immediately invoked lambda expression, IILE for short. So this is where we have a lambda expression and we immediately invoke it. So for this one, we have a lambda expression and we immediately invoke it with an index sequence. And there's a slight error on this code in this code where because it should make index sequence t minus v. So then we can get, so all we want out of this is to get all the indexes up to t minus v from 0. And it looks like that, except until t minus v. So here we just return a subtuple, and we get all of the indexes that are within the range v to t. We just expand the pack so we can get all of the elements out. So now we can use this, and it's nice using C++ 17 CTAD, class template argument deduction. We can have subtuple t, and we can have these elements C, 42, true, false, 4, and b. So we can also now have the subtuple from 2 to 4, and we can output the first element of that subtuple, and that will output 1 because it is true. Okay, so the benchmark of this is on quickbench.com. This is the link to the godbolt, and that's the link to the quickbench. So transform on a tuple. So this transforms a tuple using a lambda expression and returns that tuple that's been transformed. So it's the same as before, except we haven't got the two indexes t and v. We've got a lambda instead, and then the immediately invoked lambda expression is the same, but the name is obviously different. So here, what we do is return a subtuple again, and so for all of the elements in that tuple, we call lambda on it, and then that lambda will return us a will return us a value depending on the input that we've given it. And using C++20 concepts, we could constrain it so that it has to, calling lambda with a value must return another value. So here is a use case for transform. We can have a simple struct foo that has a constructor that just assigns the value in the constructor to the data member value, and then we can have the main function where we make a tuple t of C, 42, true, false, for, and B. So then we can make a tuple 2, which is transformed that tuple. So transform, we pass in a non-type template parameter, NTTP for short, and we make all of those elements in tuple t into a foo. So with just these lines of code, we can turn a whole tuple into foo. It's a very nice feature. And then we can output the first element, which will be C as before, because we're accessing dot value, which is a public member. So here is the benchmark of this. That's the link to the godbolt and the quick bench. So now for each. So for each is really quite similar to transform, except it doesn't return another tuple. It just calls lambda for each of the elements. So we have the same as before, as transform, just a different name. At this current slide, we have the immediately invoke lambda expression as well. And now what we do, we use this lovely C++17 feature, which we can get all of the indexes out of tuple and call it on lambda, and then just expand that pack. So a use case for this. So we can have a tuple t of, again, the same elements, and for each we can output them. That's the link to the godbolt. So now onto enumerate pack. This is a very cool trick, which you can, which is I would say really quite similar to for each, actually, because all you're doing extra is you're passing in the current index. So first of all, we have we don't have any template parameters here. We just have a pack. So the difference between enumerate pack and for each is that, well, one of the major differences is that enumerate pack takes a pack instead of a tuple. But you could easily make enumerate pack into one that would work for a tuple, calling it with all the indexes. Okay, so enumerate pack takes a callable as the first argument, and then a pack called pack. And then we have an immediately invoked lambda expression in which we call it with an index sequence. So from 0 until the size of pack. So now all we do is we call the callable with the indexes and the pack. Because the indexes and pack are the same length, we can just expand them with the same dot. So really quite simple. So an example use case for this is making a std tuple t of the same elements as we've used previously, and now we can print. Oh no, sorry. So it wouldn't be we wouldn't need that tuple there. So what we do is we make a enumerate pack. We pass in the callable, which takes two parameters: t, the index, and b, the element, and then we can print the index followed by a colon followed by the element, and then we can pass in all of the pack. So now here's a benchmark for that. This is the link to the godbolt and the quick bench. So times can be used at times is a very useful function. Well, no, sorry, it's a struct, but it has a operator parens. Okay. So times is something that performs calls the lambda a certain amount of times. Okay. So times, let's look at the implementation. So times takes a non-type template parameter t, which is how many times we're going to call this callable. And then with the operator parens, it takes in a callable, which is what we'll be calling t times. Then we have the immediately invoked lambda expression, and we just we can call the lambda with the indexes and the we can call the lambda. So call lambda just takes in an index and takes in the callable and the index and just calls the callable. We need to pass it to another one because we need to expand the pack. So this stops us doing recursion. So the reason we call it with indexes is because we need somehow to expand the pack t times. So we have to delegate to a context with function call lambda, and then we just discard the index and we just call the callable. So it's a very, very useful feature. So now we can use it like this. So times 10, and we can just print hello 10 times. The benchmark of this, and the golf ball, and the quick bench. So stay tuned for part 2, and see you next time.